In this video, we're going to talk about Laplace transforms, probably the most important mathematical tool that you will use in a control systems class. Laplace transform, you probably have already encountered it in a differential equations course, and for most students, the Laplace transform operation on a time dependent variable, f is a function of time. The Laplace transform is illustrated by this integral operator where you take the time dependent variable multiplied by this exponent term and integrate this term with the limits 0 to positive infinity. This integral right here is quite intimidating for people who first see Laplace transform, but I want to uh, I want to assure you that over the course of the entire controls class, you will not be doing this integral every time, and I'll show you how. I'll show you why. So basically, if you look at the mechanics of this integral, since you're going to be integrating with respect to time and apply the limits 0 and plus infinity, you will get rid of the time variable. Instead, you will notice that f becomes a function of s, which is also called the frequency domain. And just for just for case of simplicity, I prefer writing my Laplace transform functions in uppercase, so it helps me distinguish from the non-Laplace transformed version. Okay, now what is the point? Why all this hassle? This integral operation. How does this help us? So many whys. I'll try to address those questions. First off, by taking this Laplace transform of a differential equation, you can take an ordinary differential equation, you take the Laplace transform, and your ordinary differential equation turns into an algebraic equation. Now, we all know that algebraic equations are much easier to solve compared to ordinary differential equations. So once we have that algebraic equation, we can obtain the solution to that algebraic equation. Now this solution is going to be in the frequency domain, but we're usually interested in the solutions in the time domain. So we do an inverse Laplace transform, and we get our solutions in time domain as functions of t. Okay, both the Laplace transform and the inverse Laplace transform will be performed using tables. Now if you go to your textbook, in any good differential equations textbook, you should find a list of all the important functions that have already been Laplace transformed for you right here, for example. So basically, this entire table is the solution to this integral that I've highlighted here. Okay, and there's also another significance of Laplace transform when it comes to control theory. Now I'll just state these facts for now, and as we solve problems, I will be able to further illustrate these points. Laplace transform helps us identify the oscillatory behavior of your output to input, and it also is able to capture exponential behavior of your output to input. So when it comes to analyzing the stability of a system, the stability of a dynamic system, Laplace transform will be able to tell you whether your system is going to oscillate or whether your system is going to exponentially increase or whether your system is going to exponentially decay. So for dynamic systems, the algebraic equations generated from Laplace transform can be analyzed to predict whether we're going to have an oscillatory response or an exponential response. Both being of extreme interest to a controls engineer. So we've been talking about theory, so let's illustrate the mechanics of Laplace transform by solving a first order differential equation here. Okay, and the initial condition, for simplicity, I'm gonna put 0. Okay, so we start off by taking Laplace transform of the left hand side and the right hand side. Now since Laplace transform is a linear operator, you can distribute Laplace, the operator, on both terms, and you can bring out the constant terms. So this becomes 2 times Laplace transform of the derivative term plus 5 times the Laplace transform of y equals negative 8 times the Laplace transform of e to the negative t. Again, just to repeat, all I've done is taken advantage of the fact that the Laplace transform is a linear operator, so I've been able to expand it and factor out the constant terms. Okay, so I'm going to further expand the Laplace transform of derivatives. So the Laplace transform of an nth order derivative can be written as s raised to power n times y minus s raised to power n minus 1 times y at t equals 0 minus s times n minus 2 times the first derivative, also evaluated at t equals 0, and this goes on till you reach s raised to power 0, so just 1 times y, the n minus first derivative, evaluated at t equals 0. So for a first order, so just for a simple dy dt, this will come out to s times y of s minus y evaluated at t equals 0. Okay, and the proof of this relationship can be found in your textbook. And here we can take advantage of our initial condition that we specified earlier, which means that y at t equals 0 just vanishes. Okay, so the Laplace transform of our first term is going to be 2 times s multiplied by y of s plus 5. The Laplace transform of y and t will just be written as uppercase y equals negative 8, and to evaluate the Laplace transform of e raised to power negative t, we will take advantage of table 7.1 here, and you can see that the Laplace transform of e raised to power a to the t will be 1 over s minus a. So for e raised to power negative t, it should be 1 over s plus 1. Alright, so once I factor out y of s, I'm left with 2s plus 5 equals negative 8 over s plus 1. Y of s equals negative 8 over 2s plus 5 times s plus 1. Now, in order to take the inverse Laplace transform, I'll have to further this decompose this rational function into its partial fractions, which will take the form a times 2s plus 5 plus b times s plus 1. Now, I will not spend time evaluating these constants. I'll leave that up to you as an exercise, but at this stage I'll just treat them as constants and factor them out when I take the Laplace inverse. So by taking the Laplace inverse, let's see what we get. Laplace inverse, curly brackets. So y of s goes back to y of t. Alright, a can be factored out, and 1 over 2s plus 5. Let's see how we can deal with that. Alright, we're looking at something of also, let me simplify this first. I'm gonna I'll take a over 2s plus 5, factor out the 2 from the bottom, and this becomes a divided by 2 becomes a new constant. So I'm left with s plus 5 over 2. So a prime times the Laplace inverse of 1 over s plus 5 over 2, or if you're more comfortable, I'll just write it as a over 2 plus b times Laplace inverse of 1 over s plus 1. Now, going back to our table, 1 over s minus a, both of these terms are 1 over the reciprocal of a linear expression in x, so they're going to have a exponential inverse in the time domain. So for the first term, it's going to be e raised to power minus 5 over 2t plus b raised to power e to the minus t. Alright, and so notice how both of the exponent terms have a negative here, which means that y, whatever the value of y is, it's going to eventually decay over time. Alright. So having negative exponents in a control response is desirable to achieve stability. And we could have already, in our expression earlier, once we get fluent in Laplace transforms, we can recognize our exponent terms easily in the algebraic expression, and we won't need to go all the way to the final time domain solution to assess the stability. Similarly, if we have functions of the form higher order reciprocal functions of s squared, we can assess the oscillatory nature of our transform, of our expression. Alright, to sum it all up, the Laplace transform takes a time dependent variable into the frequency domain. And the reason it's helpful is it takes the ODE, turns it into an algebraic equation, which we are able to solve, and then by taking the Laplace inverse transform, we can get the solution in the time domain. And also the algebraic expressions that we're able to generate here can allow us to assess the stability of our system. All right, mainly the if you have a polynomial term in the denominator, the roots of this polynomial are what's essential to the analysis of stability, but we'll get to that later in this class. So hopefully this was helpful, and I'll catch you guys next time.